Okay, so hello and welcome to this video. If you're new to the channel, welcome to the channel, but if you're visiting back, welcome back. This is part 2 of the communication subsystem design. Part 1, we designed the flowchart that we will follow to have the subsystems for the comms board working, and in this one I'm going to go into the circuit design details and implement a very basic but functional board or circuit or schematic that will help us achieve the intended functional requirements as we discussed in the last video. So right here I have outlined a few items that need to be designed. First, we have the MCU, LORA antenna, the flash memory on the comms board, LEDs, the brownout reset circuit, the inhibit switches, and the CAN bus. This CAN bus is like a bonus. I might not add it yet, but I am going to discuss a few items here that I think we have done them in videos before, so I don't want to keep repeating the same design procedures. But basically, starting with the MCU part, I've decided to use a STM32F103 board, which is pretty basic to help me handle any communication functions I need. So this is the STM MCU, and obviously the STM or any MCU for that matter requires 4 things basically. So it requires a source of power, power supply, a logic level most of the time. It requires a clock or oscillator. Some of them have internal oscillators, but we'd rather use an external oscillator. So I've placed a 16 megahertz high-speed external clock here, connected to the oscillator in and oscillator out pins of the MCU at this point, right? 3v3 power supply is coming from the EPS board, the electronic power supply board. I think I should note that this is 5 volts from the EPS. Comes in here and gets regulated down to 3.3 volts. Now the reason I did this regulation, I can as easily send 3.3 volts from the electronic power supply board, but I want this design architecture to have dedicated power supplies, or rather regulators on themselves. So in case the 5 volts, the 3.3 volts on the EPS fails, I'll know that the source of failure is on the EPS. But if I get 5 volts from the EPS directly, I can easily pinpoint. The boards can be independent. That's what I'm trying to say. The boards are independent basically. So this is a basic decoupling of the power supply as recommended from their data sheet and from any design. The third thing is a way of programming this chip. So I have placed a boot enable, or rather boot select pin here. So 3.3 at ground. When it's 3.3, can be in programming mode, and its ground can be in run state. So this is connected to this pin, and you can be able to select and upload your program there. So what's missing is the SWD pins that I will add later as we go on. And then the next major thing that we need to have is now the telemetry, or rather the communication module itself. So I've chosen to go with the LORA module here. This is the LORA module E22400 eByte. Basically I call it eByte, rather it's called eByte. So just to show you what that module is, I'll just search it on LCC and open So this is a module right here. This is a module. If I open its datasheet, we open its datasheet, and yeah, you can see it's a LORA chip for 33 megahertz and for 70 megahertz. Specifications: power supply maximum 5.5, which is okay. Typical is 50. It's recommended to use 5 volts. Okay, so communication level is at 3.3 volts. So I think I'll have to correct that here because I supplied it with 3.3. Okay, so I'll have to correct that part. But communication level is 3.3, so we don't need a level converter from this chip to this chip, because STM32 uses 3.3 volts. This communication level is 3.3 volts, so which is fine. Basically, if we had 5 volts and 3.3, we need a level shifter in the middle here, but so this saves us a lot of trouble. Operating frequency typical is 433 megahertz. Let's see. All right, cool. The pin out, mechanical pin description. We have all these pins. Basically, I'm using SPI communication to link this LORA chip to the STM, so you can see the. Let me rename this to LORA. You can see the LORA chip select SDK MISO-MOSI connected to SPI1 of the STM32, and then they are connected at this point, plus also some other utility signals like the reset, busy, and DIO1 and DIO2. Also transmission enable and RX enable as described in the data sheet. Yeah, so for example, RX enable is used to switch the receiving control pin, right? So you can turn on and off the receiving and transmitting, which means for my software or firmware, we can be able to make this module sleep. So in our design architecture, we will see that we will need to have states that need to conserve power, right? So it means that if this LORA module gives us the ability to turn on and off the module, works for us perfectly. All right, so VCC power supply 2.5 to 5.5, which actually I don't think that I need to change this because 3v3 is fine, although they are recommending in the electrical parameters they are recommending to use 5 volts, but down here they are saying the range is from 2.5 to 5.5 volts. And we'll see how that goes. DOA design, they have given an application diagram. It's very basic actually. VCC and DIO pins are connected to a header right here via the SPI ADC. I think that's about all about this module for now. Software programming, we'll see that when we come to build the firmware for this comms board. But for now, we are good. Ceramic capacitor is right here. Let me check the value that they are recommending. It's fine. External ceramic filter is fine. So I use 100 NF for high frequencies. All right, cool. So let me see about this reset pin, chip reset trigger valid low level. Okay, so this is a reset pin that when you hold this pin for a few, I think milliseconds or microseconds, this chip will reset. So I've used a transistor drive right here, very basic one, to help me reset this chip. So when I pulse this pin, turns on this transistor pulls the pin to ground. You can see it's active low because of this N right here, N reset makes it active low. Alright, cool. So let's go on with this. Let's finish this design. So what I need to do first is open the datasheet for the STM32 chip. So I'll just look for it right here, put the part number and open open the datasheet. Let me download that, desktop, save, open. So what I'm looking for is the SWD pins. No, should look for it here. SWD. Okay, cool. So this is PA13, is DIO, SWDIO. There are usually 4. Then clock is PA14. So that's all I need. So PA14 and PA13. Where are they? Right here. So we put that there, PA13, I'll put it right there. Then we add net labels. This is a programming header, so I'll say this is SWDIO. Then this is SWD clock, right? PA13. Clock is PA14, sorry. Clock is PA14, so I changed those two right about there. We'll make this schematic neater later. So I need a 4-pin header right here to do that. So I'll just look for it on LCSC. So this is 2.5 mm HDR pin header. Let's see. Yeah, this is the one I'm looking for. So I'll just take that directly, copy the part number, come over here, Shift F, paste, and paste. So this should be right there. So I want to place this as 3.3, place this as clock, and then these two, and that one I'll use them as the serial wire debug pins. Okay, so that's that. Let me place it, let's see, let me place it at the top here. Okay, that's okay. So the other thing we need to add is flash memory. Let's add the flash memory. You have the MCU, LORA comes with its antenna, then the flash memory. So if I open the OBC, I believe I have a flash memory somewhere. Yeah, so I'll use the same flash memory. This is 128 megabits, right? 128 megabits, which is around 16 MB. So 128 MBs to just divided by 8, so 16, right? 16 megabytes, 16 MB memory. So I don't need to change anything. I'll just copy this as it is and paste it here. Paste it right there. Just move these a little bit. 3v3. This is supposed to be this 3v3, so I'll just take 3v3 here, paste. So a filter is always necessary for the flash memory, for example. Now MISO, MOSI, and SEK remain the same, and what I need here is the flash chip select pin. So I can put that somewhere here. Later on we'll confirm these pinouts with the STM32 cube ID. It's actually recommended to start from the STM32 cube ID, assign the pins, and then assign them here on the schematic. But for now, I don't want to run the cube ID yet. I'm sure these pins are okay as they are. We'll review the schematic later. So the next thing that we add is the LEDs. Let's add some LEDs here for just user indication LEDs. The good thing is I can reuse a lot of components that I have used to design this on board computer board, so that it actually makes manufacturing way easier when you do that. And the cost of buying components distributes all the component part numbers across the BOM, so you don't have to like resolve component that some component is out of stock or whatnot. So yeah, I think that's the advantage of reusing these components. So I'll just take a schematic like this one for the LED resistor and LED and place them right somewhere here. I need like 4 of them. Let's see. Yeah, I need 4. I can use an RGB, but you know, it's cheaper and easier to do this. Connect them to ground, and then I'll just rearrange these pins, or I can rename these to LED1, LED2, and LED3. Okay, 1, 2, and 3. And then these pins, I connect them to the controller. So I'll just put this one right there and this one right about there. Make this one neater a little bit. Okay. So label the nets. This is LED 3, right? LED 3, 2, 1. So place that and place that. This is 1. This is 2. Okay, let's connect them to the STM. So I'll take this P8 and connect them there. And this other one. So LED1, LED2, LED3, right? 2. And remember, these have no functional. Of course, they have a functional use, but they are just for me to use to debug. It's always advised to have a spare LED or a spare button to test your inputs and outputs first. Plus, I can use them to show different states, you know, of operation. I can pulse them at different frequencies to show maybe a failure, success of some message transmission, etc. So that's why I'm adding these LEDs. Yes, someone might say that they add the cost of the board. Obviously, yes, they do. But since this is a prototype, I have like a margin of cost that I can use, right? But if it was a production level board, you would cut all of these unnecessary components, right, to make the board cheaper, right? But yeah, let's just work with that at the moment. Plus this helps you to design. This helps you in DFM. So when you're designing for manufacturing, you want to make sure that before you go to manufacturing, your prototype is tested fully, right? It's tested fully. You just can't jump from an idea to execution to manufacturing directly. But I mean, the cost of an LED is negligible, if you ask me at this point. Okay, so LEDs, BOR, brownout reset circuit, is a circuit that is used to reset the chip when the power supply goes below a given voltage level. So when you power cycle an MCU or a chip, basically it has to know the state that it is starting at, right? What level are the pins at, especially on the voltage side. So if it's starting at if it's supposed to use 3.3 volts, you realize that if you go through most data sheets of MCUs, you realize that they give you what is called what's the word? But basically they have a time between turning on the MCU or the power supply and the voltage level stabilizing, right? Stabilizing. I think I can show you that from the ESP side. ESP32 data sheet. I don't know. Let's see whether this one has it. Functional timers. Let's see. Is it electrical characteristics? Let me search for chip. Power supply. Yeah, chip power up and reset. Good. This is the diagram I'm talking about. So you see, the power rails need a short time to stabilize, right? So this short time allows the chip before it sets the pin to anything that it needs to set them to. The voltage level will have reached the given or the desired voltage. Now, where does the brownout reset circuit come in? Let me use the one that I've used on the OBC to explain. So what happens is that if you have a voltage that you are monitoring here, 3V3, for example, this is the APX 809S29. So if you look at the data sheet, which I will not look at this point, this 29 represents the voltage level at which this chip will generate a reset signal to the chip. So this is 2.9 volts. So if the supply voltage goes below 2.9 volts, we generate a BOR reset, or rather a reset signal that goes to the reset pin of the MCU. So this signal comes all the way to this point. It just resets, like pressing this button, resets and reset, and the MCU power cycles, right? So for a CubeSat, it's recommended that you don't have to, you must have a way of resetting the MCU in case of anything, and in this case, in case of a power supply brownout, right? So in the firmware, we will see that you also need to reset the chip in case of software hang. That's where the watchdog timers come in. Okay, but right now I will connect this BOR. I'll just reuse it, the BOR circuit that I have on the OBC, to the reset pin of the MCU. So what this one needs is, I need to bring the reset signal to here, right there, and there's one more resistor that is required. Okay, no, it's not required. This is for the watchdog, so the 0 ohm watchdog. Anyway, this is the OBC. I don't want to talk about that now. So yeah, this is the brownout reset circuit. It's very simple. A very simple function. These are voltage. They are put in the category called the voltage supervisor ICs, right? Voltage supervisor ICs. Okay, cool. So let's see what else is remaining. Inhibit switches. I'll add these when I'm done with all the boards, so that we know what number of them to use. CAN bus is also a bonus, but I don't need to add it at this point. I figured that I should add it, but considering the cost of producing these boards, I don't want it to go overboard. Pun not intended. So yeah, let's see. Okay, so I was to fix the 3.3 voltage here. So if the manufacturer recommends me to use 5 volts, let me not be stubborn. Let me use 5 volts. 5 volts right there. Okay. Cool. All right, let's organize this schematic a little bit. I'll put some bounding rectangles. So let's start with one here and cover all of it to this point. And then we put one here for the power supply. Let me include, I should include this part also. Okay, copy this. I want to maintain the font settings here. So this is the power supply. This power supply. Okay. Next is we do the LORA one. The LORA actually, not LORA one. LORA. Right. So let me put it around there. Right there. This is the LORA transceiver. Okay. Next, BOR right here. So this is the brownout reset. Okay. Let me put these two pins or these two programmers. Let me move them down here. Okay, and then maybe pull this back a little bit. And right there. So this is program debug header. Okay, debug header. Next thing is the MCU itself. So I'll just draw from this point to, let's put it right there, that point. So it means I need to move these guys. Let me put them, let's see where, here. Let me put them up there. Okay. Let's see if they fit LED. Alright, yeah. So that's that. LED 1, LED 2, LED 3, and then I put this and say user LEDs. Okay, user LEDs. MCU. Okay, I'm moving as fast as I can so that the video does not become too long also. Oops. But in case you spot any errors, just let me know. But we'll review these schematics later on. For now, we just want a basic working template, right? Flash. This is the flash memory. 16 MB. 16 MB. Oops. 16 MB. I think it should be 16 MB flash memory, right? 16 MB flash memory. Okay, cool. Makes sense. Okay, that's that. I think this is fine. Now the remaining thing is, how do we connect these two boards together? Because this is a stack of, let me just show you what I mean here. CubeSat 1U. So if you look at, for example, these boards, right? Let me open this image in a new tab. You can see these boards are stacked together, so there's a connector that we need to add here. It's called the ISA connector, right? So following the PC104 standard. But for me, I will just tweak it a little bit. It does not really follow the exact standard that it's supposed to. So I have defined my own pins the way I want them to be stacked together. So for example, you see this is the ISA. That's a very simple 2.5 millimeter pitch header pin, female, but it's long enough on the male side to be able to stack the boards together. If you want more information, you can look into the Project Shadowflight GitHub repo. There's the README has described this connector deeply, plus the images are there. So this is the connector, and I'll add it to this board right there. Okay. So I need some more space. Let's see. I'll place this right there, then move this a little bit. Okay. So we bound this obviously also, just like the others, like that. Copy paste, and this is the ISA connector. Cool. So what signals do we need to pass from this board to the rest of the other boards, right? So you see this is 5 volts from the EPS. For example, I have to rename this to conform with whatever is being received from the connector, right? Okay, so I said again in the first video that this is going to communicate to the OBC via I2C, right? I2C. So I need I2C communication here, right? Which is already there. I2C is already placed here. Okay. So I need the I2C pins on the STM32 F103 board. Luckily, obviously, let's see on the data sheet where the I2C1, for example, is placed, which pins it is placed. Let me just search it. I2C. Okay, I2C2 is on PB10 and PB11. PB10 and 11 are those being used? Okay, 10 and 11. So I can move this guy maybe up here. Delete that. Then this should be PB11 is I2C2 SDA. Yep. This is SDA, right? And then this other guy is SCL. PB10 is SCL. So SCL right there. SCL. All right. So yeah, that's that. So we have coupled from this ISA connector to this connector. What else might we need? I think that's all we need from this board. That's all we need from this board, actually, from the comms board. This is my MCU on the OBC. I'm thinking if I can route also, but I don't need to route these pins from the LORA to the OBC. That will be the whole purpose of having an MCU here. Okay, so there's another pin we need. We need to have board detect. How do we know that this board has been inserted into the how do we know that this board has been inserted into the cubesat stack, right? So to do that, we just add a resistor to ground, right? 10k resistor to ground. Where is it? I'm looking for a 10k resistor. Yeah, like this one. Place it right there and then connect it to ground. Okay. So how does this work? Let's add a label first and then I explain how this part works. Let's say comms board detect. Okay, comms board detect. It's too long. Comms board detect. So this pin comes right here to a pin on the IC connector, and then it's routed from this pin. It's routed to this connector here. Then from this connector here, it goes to the MCU, right? So how it works is this, very simple. When you insert this comms board, this pin will be pulled low, right? Because of this resistor. So on the OBC, you can sample, you can read this pin, this GPIO, and see is it low or high, yeah, or is it low or floating. You can use the internal pull-ups also, and if it's low, we know the comms board has been inserted. Okay, so that board is simple as that. I'll place this here, comms P2, no, there's P3. Okay, so yeah, that's that. Pretty basic design, but it will do the job of having the MCU and the LORA communication part. I think there are some other things we need to add, obviously, like the in-bit switches for the cubesat standard, and yeah, this should be fine. LORA receives commands, processes them over here, then sends them over to the OBC via I2C, and then some of those commands can be saved, or other those commands can be saved to the flash memory. We can retrieve the flash memory also from there. This, you can retrieve commands from the flash memory, right? So if you realize, one question is, no, actually there's how do we pass SPI signals from the OBC to these other boards? So I think we should add, just like we have added the I2C, I think we should add the SPI connection on the ISA connector also. So I'll do that. We need 3 pins. We might need some slaves, so I'll do that, but first I'll connect the standard SPI pins, and then in case I want this device to be SPI slave from the onboard device, I should have a slave pin somewhere here. So let me have it. Comms CS. Okay, so yeah, so that means that as I conclude, this MCU can become an SPI slave, or we can use the I2C communication. We'll just experiment with all of them and see which works best. So it's best you have the hardware should be able to handle, you know, your predicted ideas, right? So yeah, so this comms board can become a slave also, and then I think it can become a master to these onboard SPI devices, but I'm rooting for the I2C one, which is it's easier and it's more defined. Rather, for this setup, it's more defined. Okay, so yeah, there we go. That's all about this comms board design part 2, and I'll see you on the next video, maybe when we'll be reviewing this exact board or designing a new one. Otherwise, all the best, and yeah, see you later.